The Adventures of Mr Tompkins was created by George Gamow, the renowned physicist who first proposed the physical model of the universe known as the Big Bang Theory. He is perhaps best known around the world for having created the curious and lovable bank clerk, C.G.H. Tompkins, a bank clerk who dresses as if he's the president of the bank. His understanding of mathematics is limited to the operations of addition, subtraction, multiplication, and division, of which he uses only 2. Nevertheless, he has a passion for attending science lectures. After the lecture, he goes home to bed and dreams that he has been transported, pajamas and all, to the time and place where these celebrated scientists lived and worked. The next morning, Mr. Tompkins wakes up enchanted by his new understanding of science. Igor Gamow is George Gamow's son and the creator of the Mr. Tompkins film series. Igor has worn many hats. The white hat of a cowboy hero, the black hat of the villain, motorcycle hat of a White House courier, and a feathered hat as a member of the National Ballet Company. Today, he wears the hat of a professor.
Good evening. Tonight's lecture is entitled Ernest Rutherford, The Anatomy of the Atom. I can give you a quote, a direct quote from one of his biographers. Ernest Rutherford is one of the most illustrious scientists of all time. He is to the atom what Darwin was to evolution, what Newton was to mechanics, what Faraday was to electricity, and what Einstein was to relativity. He is known for many, many experiments. I'm going to list you 4 of his major discoveries, any one of which would have won him, and did win him, actually, a Nobel Prize in 1908. His first great insight was to explain that radioactivity, the work that Marie Curie had done, in fact she coined the word radioactivity, was the disintegration of the atom. His second major discovery was the anatomy, that he was able to describe the atom like any child, school child now knows that an atom has all the negative electrons on the outside, has a positive nucleus on the inside, and a lot of space in between. Before Rutherford, we had a completely different model. And additionally, he was the world's first successful alchemist. Alchemy has been around for centuries and centuries. People tried to, including Newton, to take one type of atom and transform it into another type of atom. Obviously, the driving goal was to take something like lead and turn it into gold. Everyone was unsuccessful, and therefore the sort of a scientist always said that all atoms were created at the beginning of time and were unchangeable. And finally, he was able to use radioactivity in order to determine the age of various objects, i.e., every radioactive atom has a half-life. The most popular one we all know, of course, is carbon-14, in which you could determine how old ships and old trees and old stumps, but there are many, many radioactive atoms, and they all have a half-life, because as he discovered, each of these radioactive atoms will spontaneously and with no predictability disintegrate, leave off an energy which tells you a little bit about the time. I want to tell you a few things about his early life. His family came from, in 1842, came from Scotland, from a small place called Perth, and he arrived in Nelson, Australia, his father, who was a wheelwright. I had to look that up in the dictionary. A wheelwright is a person who makes and fixes wheels. And they started a family in a little village, Nelson, in the South Island of New Zealand. And his father had 12 children, 7 boys and 5 girls. Little Ernest was the 5th child. And he was a bit precocious. He was, from the very beginning, interested in science and math. But for the most part, he worked on his family farm, and he was picking and growing potatoes. He did get a scholarship to the University of New Zealand, and then he was invited to go to Cambridge University in England, Trinity College. And the person he worked with there was J.J. Thomson. J.J. Thomson, of course a Nobel laureate, was the first person to describe the electron. And his career just blossomed when he went to England. Atomic science, or maybe better say nuclear science, in the last 10 years of the 19th century was just incredible. It was just unbelievable. You had J.J. Thomson, who discovered the electron. You had Rutherford, who was a student to J.J. Thomson, who did the anatomy of the atom. You had a student of Rutherford, Niels Bohr, who introduced quantum mechanics. And finally, a student of Niels Bohr, by father, George Gamow, with the Big Bang theory of the universe. It was just an incredible period of time. I think a good analogy would be in Germany for about 100 years, a little more than 100 years, you had incredible music. You had Beethoven, Handel, Bach, Mozart, and then, boom, it was over with. But that was called kind of a German virus. I would like to think of the incredible work done by these early people the last 10 years of the 19th century to be a little equivalent to the music virus, if you wish, of Germany. Now, I have my favorite apple. This is my Newton apple. And I want to tell you the anatomy of the atom first, as described by Rutherford. And then I will give you the series of experiments in which he concluded that this was the correct model. Often professors do it the other way around. They go through a whole series of experiments, and then by the time everybody's really lost, you say, aha, and these experiments apply this model. So I'll give you the model to begin with. We'll do a little mental gymnastics. Let's take this apple, and we'll make it the size of the Earth. So you can imagine it's one big apple. Now the question is, if you look inside the apple, what are the size of the atoms inside of an apple which is the size of the Earth? And it turns out the average size of the atom is about the size of a cherry. All right? So here we pluck out the cherry, and we look inside the cherry, and you have to use a little imagination here, and you don't see anything. It looks empty. So you say, well, the cherry's a little too small. Let's blow it up the size of a basketball. You don't see anything either. All right, let's blow it up the size of a tennis court. If you look very carefully, you begin to see something in the middle. Says, oh, heck, let's blow it up the size of a football coliseum. And now you see something inside. You see a little pebble. And you see nothing else except you see a cloud of smushed electrons going around. So virtually, it's all empty. And what's in the center is what we call, and every school child knows, a nucleus. And it's positively charged. Now, very soon after Rutherford devised this model, based on very, very sound experiments, his close colleague, Chadwick, discovered the neutron. So inside the atom, you have a bundle of protons, and the positive charge is neutralized by the neutrons. So this is the model that he devised, and it's a model that we use today. But at the time he began his experiments, his boss, J.J. Thomson, was the first one to propose what he called the rice pudding model of an atom. My father never liked to eat rice pudding, so he liked watermelon, so he called it the watermelon model. But the same thing, that you have positive and negative charges distributed everywhere. And this was the ruling model at that time. Rutherford was interested in this discovery by another colleague named Henri Becquerel, who discovered radioactivity really quite accidentally. He had inherited some uranium salts from his dad, and his dad was a photographer, and you use uranium salts to enhance photographs at that time. And he had the uranium salts in the same drawer where he had a lot of photographic plates, unexposed photographic plates with black paper. And when he tried to use the photographic, he noticed that they were badly damaged, as if they had been exposed to light, all of them. And then he made the really interesting conclusion that perhaps something in the dark drawer from the uranium salt exposed the film. Now, he had a little basis of thinking that because just at that same time, in 1895, Wilhelm Röntgen in Germany, using the cathode ray tube developed by J.J. Thomson, Rutherford's professor, discovered X-rays, that there was radiation coming from a tube. When you electrified it, you had a cathode and an anode, and you could expose film or get scintillations on the fluorescent screen. So he made the jump. He said, aha, what's coming out of his uranium salts is the same what came out of this cathode ray tube done by Röntgen. And actually, he was wrong. But it started a lot of excitement because it was easy to do the experiment. Oh, you just take the salt, but it wasn't as powerful as X-rays. In the first X-rays that Röntgen did, you could take your hand, shine an X-ray through it, and the photograph that you see now is one of the most famous ones. You see the wedding ring on the hand, and everyone just went bananas over that. Rutherford decided that he would look a little further into what Madame Curie had called radioactivity. So he took a block of lead, bored out a hole in the middle, and dropped a little bit of salt, uranium salt, at the bottom, expecting that whatever radiation came from the salt would come out of the top of the block. And you can see in this picture that they had three types of rays. You have one rays who went to the left. You have one ray that went to the right. Rutherford named those alpha and beta. And another ray that went straight up. The reason that they were bending is because Rutherford cleverly put a magnet with the north and south pole of a magnet perpendicular to the direction of the rays. So he could determine that with the magnet, that what went left were positive, turned out to be alpha particles, what we now know as alpha particles, the bare nucleus of helium, and what went to the right were the negative electrons. And later on, one of his colleagues found that what went straight up was the same type of ray that Röntgen had discovered in Germany, the X-ray, but this time a much stronger ray called gamma ray. So now he had a method. Rutherford had a method of capturing the radiation in a very specific way. So he decided to do the following experiment. And it's an experiment, actually, given that you had a little radium, that any school child could do in school, compared to the experiments we do today. He had a little radium. He had a lead screen with a little hole through it. And through the little hole, he had the alpha particles come from. You remember the alpha particles being the bare nucleus of helium. Then he had various sheets of foil, of metallic foil like gold and tin, steel, very thin, and the alpha particles would go through. Now, again, with your mental gymnastics, if the atoms in the foil was like the watermelon, with a even distribution of negative, positive charges every place, you would expect the positive alpha particle, which is fairly large and heavy, it's 2 neutrons and 2 protons, to mostly go straight through, and behind he had a fluorescent screen in which every time the particle hit the screen, you got a little blip. But a little bit to his astonishment, when he did the experiment, he got a lot of scattering. He got alpha particles which mostly went straight through, but some of them were strongly deflected. And occasionally, one alpha particle almost came back and hit him in the nose. That was a bit of an exaggeration. But Rutherford was astonished. He says, it's as if you took a tissue paper and shot a cannonball at it, and the tissue paper would throw it back to you. And from that experiment, he concluded that the only way you could explain this data is that all the positive charges must be concentrated in one place, i.e., what we now as a nucleus. So the structure of the atom that Rutherford proposed, the anatomy of the atom, if you wish, with a nucleus in its center, bunch of electrons on the outside, looks very similar to our solar system when we have the sun and a series of planets, 8 or 9 planets, depending how you count. But in the solar system, you have attractive forces, that the planets, gravitational forces, and the sun holds them together. But in the experiment, in the scattering experiment Rutherford did, you have a big, heavy alpha particle coming in to a rather, this is what we're proposing, dense positive nucleus. But the unanswered question, which Rutherford wanted to answer, was in the solar system, there are attractive forces. But in the atom, there will be repulsive forces, because it's the positive alpha and the positive nucleus. And it turns out mathematically, and this is the mathematics, so it's a little bit beyond you, and it's beyond me. It's quite sophisticated mathematics. You can predict whether the scattering pattern on the screen behind suggests that there are attractive forces, like in the solar system, or repulsive forces, like we're proposing in an atom. Attractive forces would give you elliptical orbits, and the repulsive forces hyperbolic orbits. When he did the experiment, plotted the data in which you had the number of scintillations, meaning the number of little bright lights on the fluorescent screen, as a function of the angle of scattering, it exactly fit the theoretical curve that you would expect by repulsion. And so that was sort of the final brick in his model. Finally, with all his work done, he became director of the Cavendish Lab. Of course, his student was Niels Bohr, quantum mechanics, and he just had the most illustrious career. But he had a strange personality, according to some people. He was called, he would burst into a lab with song, and he loved to sing "Onward, Christian Soldiers." So the next lectures we'll be talking about would be, again, an atomic, but in nuclear physics. But for tonight, I think you've probably had your fill. So good night.
earth am I?
You're in an uranium mine in Colorado.
Why is it so dark? Am I blind?
Oh, I'm so sorry. How careless of me. Is this better? On the surface of the nucleus of a common uranium atom.
Sparkling shekels. Why, I recognize you from Professor Igor's lecture. You're Professor Ernest Rutherford.
Rutherford, at your service. Pleased to meet you, Mr. Tompkins.
How do you know my name?
Oh, I've delighted in all your adventures, Mr. Tompkins, in the series of books written by George Gamow, the father of Professor Igor. In some circles, you really are quite famous.
Me? Famous? What do they say about me? Do all the ladies like to...
Come, Mr. Tompkins, we don't have all night. You're on the verge of waking up, so you'd better ask me any questions you may have very quickly.
So, if we are standing on the surface of a uranium atom's nucleus, then I presume these balls underneath our feet are protons and neutrons of the uranium atom.
Protons are red and the neutrons are blue. But these are just abstractions for the sake of your imagination. The rather prosaic name we give this particular uranium atom is 92U238.
92U238? That's not a very catchy name. But what is that shimmering haze buzzing all about us off in the distance? Oh, wait a second, I know those are electrons.
Yes, very good. These are very, very small, and as you notice, also very far away comparatively. The diameter of the atom's nucleus is 10,000 times smaller than the total atom, the outer boundary of the total atom being the outermost shell of electrons whizzing about it. In between the nucleus and the electrons is just empty space. I trust that you have in your lecture notes that 99.999% of an atom is empty.
Right, of course. But, say, didn't Professor Igor also say that the nucleus would appear to be the size of a small pebble if the uranium atom was blown up to the size of a football stadium?
Football? Oh, yes, yes. I'm so sorry. It's so confusing when you Americans use the word football. English football is what you Americans call soccer, but I always preferred the grandfather of American football myself, rugby. Was quite a good forward during my days at Nelson and Canterbury, if I may be so bold.
Well, in any case, in contrast to Professor Igor's analogy, I prefer the analogy that the nucleus is like a gnat in a cathedral.
Well, that works too, but whether you compare an electron to a pebble, or a grain of sand, or even a gnat, they really do not even exist in a single location, as a pebble or a fly might. Instead, an electron has a finite possibility of existing everywhere and nowhere at the same time. When the cloud is more opaque, there's a greater possibility you'll find an electron. Where it's more transparent, a lesser probability.
One could probably use the analogy that the electron is like a hyperchild as well.
Yes. What a delightful analogy, my dear chap. Quite as well. Well, it takes about 150 attoseconds for an electron to orbit an atom's nucleus. What is an attosecond, you may ask? An attosecond is 10 to the negative 18th seconds long. Or think of it like this. 1 attosecond is to a second as 1 second is to the entire age of the universe.
Oh my god, that's fast. Even faster than a New York minute.
Indubitably. It wasn't until 2008 that scientists were able to record the first video images of an electron's orbit. The particle is so quick.
I think I may remember reading that somewhere. So, how many electrons does a uranium atom have then?
92, one for each proton. All the stable atoms, as a matter of fact, have an equal number of protons and electrons.
So that's why the uranium atom's first name is 92.
Yes, and while there are 11 elements with more protons than uranium, and thus are heavier, uranium is the largest and heaviest of all atoms, which exist naturally on Earth. But tell me, Tompkins, can you tell me how many neutrons a common uranium has, based on the fact that the uranium atom's last name, to use your analogy, is 238, with 238 being the total combined number of protons and neutrons?
Well, if you subtract 92 protons from the 238 total nucleons, you get 146. 146 neutrons.
Very good, Mr. Tompkins. I forgot that you're a bank clerk. Simple subtraction must be child's play for you.
Elementary, my dear Rutherford. Get it? Elementary. So I have a question about the gold foil scattering experiment that you and your assistants Geiger and Marsden performed in 1909.
Yes?
You shot alpha particles at various atoms in the foils you were bombarding. Did it ever happen that your alpha particle hit the nucleus and split it in half?
Mr. Tompkins, that is just an extraordinarily clever question. I haven't even yet discussed nuclear fission with you, and here you are bringing it up like an idiot savant. As a matter of fact, 20 years after the scattering experiment, I and my close colleagues Cockcroft and Walton performed an atom-splitting experiment. First, we decided we could not use the alpha particle because it had too large a mass, 2 protons and 2 neutrons, and it had too large of a charge, +2. So we used as our projectile a far lighter and less charged projectile, the nucleus of the hydrogen atom, a proton.
Couldn't you have used an electron as your projectile?
Yes, we thought of that. The voltage necessary to create fast electrons wasn't possible, so we